Okay, let's do lesson 9.5, factoring the difference of squares, page 501 in your book. Let's start off with understanding what the difference of squares is. It's a simple rule that says if you have a squared number minus difference of squares minus a b squared number, okay? So two different squares with a minus sign between them, they automatically can be factored to a plus b times a minus b, or you can do it in any of the order, a minus b times a plus b. Either one of those two work. Okay, let's take a look at an example of that. X squared minus 9. Well, we see right away that x squared is a squared function, x squared. But 9 is really 3 squared. And so we have a minus sign between them. So we can immediately translate that to x plus 3 times x minus 3. Or the opposite version of that. Doesn't matter in which order we put those two. Let's take a look at an example. All right, example 1a in your book. What if I have n squared minus 25? Well, the first thing I notice is that's really n squared minus 5 squared. So it's a difference of squares. And since it's a difference of squares, I can immediately take it to n plus 5 times n minus 5. And that's how simple this is. Let's look at another example. I've got 36x squared minus 49y squared. I look at it, I've got the minus sign, so if this is a square and this is a square, I can figure it out quickly. Well, 36 is a perfect square. 6 times 6 is 36. Well, x squared, obviously, x times x is x squared. So 6x squared is what this guy is. All right, 6x parentheses squared. This would be 7y parentheses squared. So I write that. 6x in parentheses squared minus 7y in parentheses squared. And since that's true, I can immediately go to the first term plus the second term times the first term minus the second term. It's pretty simple. Now let's take a look at example 2. In example 2, we have the problem 48a cubed minus 12. And in this example, I don't have a perfect square right away, so what I'm first going to do is look to see if I can factor something out. And I can factor a 12a out of that. So you don't always use a factoring method all by itself. Sometimes you use a different method first before you get to some of the other methods. So here's the first method, is to factor out a 12a. So I factor out a 12a, so 12 times 4a squared, 12a times 4a squared gives me 48a squared. I can pull a 12a out of 12a, leaves me with just minus 1. Now I realize that this is really 2a in parentheses squared, and this is really 1 squared, so I have difference of squares. So I write that as that. 12a stays there. It's outside the parentheses. I then change 4a squared into 2a in parentheses squared minus 1 squared. When I have the difference of squares, I can immediately translate that to the first term plus the second term times the first term minus the second term. So I have my original 12a times 2a plus 1 times 2a minus 1. Let's look at another example. Let's look at example 3. In example 3, we have 2x to the fourth minus 162. Okay? In this example, well, I can see right away I can pull a 2 out. So I'm going to go ahead and do that. So I pull a 2 out and I get x to the fourth minus 81. So that looks like the difference of squares to me, because I can go x squared squared minus 9 squared. So I do that. I change this over to x squared squared. X to the fourth is x squared squared minus 81 changes into minus the quantity 9 squared. So I've got difference of squares, so I can immediately factor that out to the first term, x squared, plus the second term, 9, and the first term, x squared, minus the second term, 9. But then normally I'd say, well, I'm done, but I'm not done because I look at this a little closer and I see squared and a minus and another square. So I rewrite that. The first part is all alone. The second is left alone. The second part here, x changes to x squared minus 3 squared. And that then immediately changes to my first part I keep the same, and this part in brackets changes to x plus 3 times x minus 3. And now that one is done. All right. Now let's look at the next example. The next example is example 4 in your book. And it looks like this. Down on the screen, here we go. 5x cubed plus 15x squared minus 5x minus 15. So when I look at this one, what can I don't see anything difference of squares. First of all, there's not 2 terms, there's 4 terms. So I'm going to start thinking about some other methods to use. Well, the first thing I notice is I could pull a 5 out of each one of those coefficients. So I'm going to go ahead and do that right off the bat. And I get 5 times the quantity x cubed plus 3x squared minus x minus 3. Notice I pulled a 5 out of this guy, leaves me with 3x. I pulled a 5 out of this guy, left me with a 1, which I didn't write. And the negative 15 divided by 5 is negative 3. Okay, I then follow that up and I look at it and I say, well, now I've got 4 terms, and 4 terms using my old rules is one of the things to look for my own groupings. So I look for groupings and I say to myself, well, x and x have the same coefficient, and this x squared and this over here have the same number, 3 on them. So I'm going to rearrange the writing of this so that the 3's are together and the x's together so that I can group them that way. Okay, so this is the same term. This here is the same as this one, just the x and the 3x squared have been changed the order of. Then I can go ahead and group them. So I group the x cubed minus x from here, and I group the 3x squared minus 3 because I know I can take a 3 out of this guy and I can take an x out of this guy. So when I pull the x out of this guy, I got x squared minus 1. I pull the 3 out of this guy, and I get x squared minus 1. Now I notice that my second term is the same on both places, so I can use the distributive property and combine x and 3 as the first term and use x squared minus 1 as a second term. So I do that, and I now have x plus 3. The x comes from here, the 3 comes from there, times my x squared minus 1. Am I done? I could be done, but I notice that this is the difference of squares. So it's really x squared minus 1 squared. So I write it that way, x squared minus 1 squared. Everything else I can leave alone because there's no more breaking down of that. And since I have the difference of squares, I can write this part right here as x plus 1, first term, plus the second term, times x minus 1, first term, minus the second term. And that is the solution to number 4. Now let's take a look at number 5. On number 5, we have a fractional problem. We have right off the bat p squared, let me get it down on the board here, p squared minus 9/16 equals 0. Okay? And in this equation, they're asking us to solve for p. So let's take a look. I could multiply by 16 to get rid of my fractions, but I noticed that this is a squared, and so is this. This is a squared. 9 over 16 is the same as 3 over 4 squared. So I write it that way. P squared minus 3 over 4 squared. It's a difference of squares. I immediately can do first term plus second term, first term minus second term. Still equals 0. And remember, in this problem, they're asking us to solve for p. So we use our zero product theorem, set both equations equal to 0, solve for each p-value. So subtract 3/4 from this one, I end up with negative 3/4 is my value. I add 3/4 this one, I end up with positive 3/4. So my solution set for this problem is negative 3/4 and positive 3/4. Let's look at example B in the book for number 5. It's 18x cubed minus 50x. Okay, and once again, I'm supposed to solve this equation. So I need to set it equal to 0, so I'm going to subtract 50x from both sides. That gives me 18x cubed minus 50x equals 0. I notice I can pull out a 2 and an x from both of those. So I pull a 2x out. I'm left with 9x squared minus 25. I realize that is the difference of squares. So 2x stays. It's outside the parentheses. Inside the parentheses changes to 3x squared minus 5 squared. Difference of squares changes immediately to 2x, stays out together. This part inside the square brackets changes to first term plus second term, first term minus second term, 3x plus 5, 3x minus 5. Now I have 3 separate factors that equal 0. So I set all 3 of them equal to 0 and solve for x on each one of them. And the first one I'm going to divide by 2. 0 divided by 2, I'll end up with x is equal to 0. In the second one, 3x, I subtract 5 both places. Then I divide by 3 and I get a negative 5/3 as my answer. Over on the third one, I add 5 to both sides, and then I divide by 3 and I get a positive 5/3. So my solution set is negative 5/3, 0, and 5/3. And finally, we get to kind of a more convoluted problem, more complex problem. In this problem, we're given this little example right here of a piece of paper that is 2 inches by 2 inches. And they've cut off a corner of it that is x long, x and x. Okay, so it's a 45-degree angle cut off. And they want to know, first of all, what's the equation for the area of A? Not the whole A, but the A minus the cutoff portion. Well, the whole square is 2 by 2, or 4, and we just have to subtract the area of that little triangle right there. Well, the area of a triangle is 1/2 base times height, so 1/2, and the base and the height of this triangle are x, 1/2 xx, or 1/2 x squared. Okay, so that answers that question by saying the whole square, 4, minus the triangle, 1/2 x squared, and that's the equation for the area of the A area, the piece of paper that's left over. Well, they go on to say, find x so that 7/9 of its original size, so that it is 7/9 of its original size. Okay? So we have to say the area that we're looking for is 7/9 of its original size. Well, its original size is 4, so I plug that in onto that side. And A, we figured out that its calculation is right here, so we plug that in on this side. And then we just solve for x. First thing I'm going to do is change this over to 28/9. Then I'm going to subtract 28/9 from both sides, leaves a 0 on this side, and you can see it, I subtracted 28/9 here. Now I'm going to change the 4 to 36/9, so I have common denominator. 36/9 minus 28/9 leaves me with 8/9. I still have my minus 1/2 x squared, and the whole thing is still equal to 0. And I look at this, and I say, well, it could be squares, the difference of squares, but it isn't. There's really nothing that 1/1/2, there's no real square root of that makes sense as an integer. So I'm going to get rid of my fractions. I have to get rid of the fractions by multiplying by 18 on both sides. 18 is the common, or least common denominator of these two. So I multiply by 18 on both sides. Well, 18 times 0 on the right-hand side just leaves me with 0. 18 times 8/9 gives me 16. 18 times negative 1/2 x squared gives me 9 x squared. Now I look at it and I see difference of squares. 4 squared minus 3x squared, 4 squared minus 3x squared, okay? And that leaves me with the final solution, or the final factoring, of 4 plus 3x times 4 minus 3x. But remember, I'm supposed to solve this equation for how big that size of x has to be, of that cutout corner of my paper. So now I need to solve for x. I need to set those two equations equal to 0. So here's that. Okay, so now here we are with the two equations from example 6 that we finished up with factoring on. And there they are, 4 plus 3x and 4 minus 3x. Both are set equal to 0 using the zero product theorem, because we're trying to solve this equation for how much of that piece of paper we're going to snip off in the corner. Okay, so I subtract 4 from this side right here, and I subtract 4 from this side, left with 3x equals negative 4, or negative 3x equals negative 4. I then divide by 3 here, I get negative 4/3. I divide by negative 3 here, I get positive 4/3. And I look at my problem and I say, this is how much paper are we going to cut off? We can't have a negative distance, so my final answer is 4/3 of an inch is the value, if you remember the original problem, of how much we're going to cut off of this piece of paper. 4/3 of an inch cut off here and here makes the area 7/9 of the original area.